In this video, I am going to explain RL circuit synthesis problem using the first form. In the example, RC impedance function is given. You know the impedance function of RC network is equal to the admittance value of RL network. Then we can write ZRC in S domain is equal to admittance value of RL network. Then the admittance value of RL network we can write S plus 1, S plus 3 over S times S plus 2. We have to use the first form to construct the RL network. Then we have to apply the partial fraction expansion for this admittance function. In first form, we are using partial fraction expansion. In a previous video, I obtained the partial fraction expansion of the RC impedance function. I will include that link to the description. You can watch it. And this is the partial fraction expansion of the RC impedance function. ZRC is equal to 1 plus 3 over 2S plus 1 over 2 times S plus 2. And these are the small impedance value in RC function Z2 and Z3. Now it is equal to the admittance value of the RL network. Then 1 plus 3 over 2S plus 1 over 2 times S plus 2. These are equal to small admittance value Y1, Y2, and this is Y3. Now we are constructing RL network. Then we have to get an idea about the impedance and admittance value of a resistor and inductor. For a resistor, impedance value of a resistor is in S domain, it is equal to R, and admittance value we can write 1 over R. And if we consider inductor, impedance value of that one is in S domain is equal to SL, and admittance value it is equal to 1 over SL. Then we can consider these Y1, Y2 and Y3 and find what are the components represented by each and every small admittance value. First I consider the Y1. Y1 is equal to 1. There are no any S terms. Then it will be a resistor. Resistor R1. I name it as R1. It is equal to 1. Then I consider Y2. Y2 value is equal to 3 over 2S. Now you can see there is a S term. Then it will be a inductor. I rearrange it 2 over 3 S. Now this one is similar to 1 over S times L. This value is the inductor value. Then this representation is an inductor. L1 is equal to 2 over 3 Henry. Then I consider the third admittance value Y3. It is equal to 1 over 2 times S plus 2. I expand it 1 over 2S plus 4. If we check this representation, we can't easily find the component represented by this Y3. Then I consider impedance value Z3 is equal to 1 over Y3. Then I can write 2S plus 4 over 1. That means 2S plus 4. Then these are the small impedance value. I name it as ZA and ZB. If we consider ZA, you can see there is a S term 2S. If we check the impedance value of an inductor, you can see it is representation of SL. The inductor value is L2 is equal to 2 Henry. Then I consider ZB, it is equal to 4 and there is no any S terms, then it will be a resistor, and impedance value of a resistor is equal to R, then R2 is equal to 4 ohm. Then these two components are connected in series because of this plus mark. These two terms are joined with plus mark. That means these two components are connected in series. Then if we consider Z3, we can draw inductor and resistor. They are series. L2 2 Henry and R2 is 4 ohm resistor. We can obtain the Z3 between these 2 points. Then if we draw the final circuit diagram, Y1 is a resistor, Y2 is inductor, and Y3 is combination of resistor and inductor. These are plus marks. In admittance, this plus mark means they are connected in parallel. Then we can draw the final circuit. First element is resistor, and the second element is inductor, and the final element is combination of inductor and resistor. We can draw like this. R1 is equal to 1 ohm resistor, L1 is equal to 2 over 3 Henry inductor, and L2 is equal to 2 Henry inductor, and R2 is equal to 4 ohm resistor. We can obtain the final impedance value using these 2 points YRL. This is the final circuit diagram that is represented by this admittance function. This admittance function, we can draw the final circuit diagram like this. I hope you all are clear about that explanation.